Last time, we looked at how programs run using processes and threads. But today, we are going deeper. We are looking at the actual scene of crime for almost every major hack in the history. That is, memory. If you want to decode how systems are actually compromised, why programs crash, what undefined behavior really means, and how exploits are even mathematically possible, you have to understand memory. Because at the end of the day, a program really only does two things: it reads the memory and it writes the memory. So let's break it down. Imagine memory as a massive, endless wall of post office boxes. Every single box has two things: an address, so you can find it, and the actual data inside. Programs don't just run magically. Your variables, your passwords, or your cat photos, and even the code of the program itself, all lives in these boxes. Execution is just your CPU looking at an address, reading the instruction inside, and doing what it says. But here is a massive security problem. If every program running on your computer shared the same exact wall of boxes, it would be a pure chaos. Your web browser could just peek into your password manager boxes. A buggy calculator app could accidentally override the operating system boxes and crash your whole PC. To fix this, the operating system pulls a brilliant trick called virtual memory. Think of virtual memory like putting a VR headset on every single process. Physically, there is only one stick of RAM, but virtually, the operating system tricks every process into thinking it has the entire memory space all to itself. Process A literally cannot see process B's memory because to process A, process B does not even exist. Okay, so a process has its own private memory. But it's not just a messy pile of data, it's strictly organized. The two most important neighborhoods in this memory are stack and the heap. The stack is your short-term notepad. It's used for function calls and local variables. It is incredibly fast, perfectly organized, and cleans up after itself automatically. But it has a rigid structure: first in, last out. The heap, on the other hand, is like a massive storage warehouse. It's used for dynamic data, stuff where you don't exactly know how much space you will need until the program is actually running. It is flexible, but it is entirely manual. The programmers has to request space and remember to give it back. So, stack is fast and strict, and heap is flexible but dangerous. Now, here is where vulnerabilities are born. Programs assume boundaries will be respected, but older system programming languages like C and C++ prioritize raw speed over safety. They trust the programmers blindly. Let's say a programmer asks the heap for a box that fits 10 bytes of data, but then a malicious user typed in password that is 20 bytes long. Does the memory reject it? No. Memory does not understand your intentions. It only follows instructions. So the program stuffs the first 10 bytes into the box, and the extra 10 bytes just spills over, crushing whatever in the box's next door. And this is buffer overflow. But why is spilling data so dangerous? Because what if the box next door wasn't just random data? What if it is a return address, the exact instruction telling the CPU where to go next? By overflowing that particular buffer, an attacker can override that instruction. Instead of the program returning to its normal job, it reads the attacker's fake address and jumps to the malicious code. You just hijack the execution flow, and you are the captain now. You can go wherever you want. So, to sum it up, program lives in the memory, and the operating system isolates them using virtual memory. Inside, they use the stack and the heap. But if languages lets you ignore the boundaries, attackers can overflow data to hijack the system. So memory safety is quite literally the foundation of cybersecurity. But if memory is isolated, how does a program ever talk to the outside world? How does it even read a file or send a network packet? That requires crossing the ultimate boundary with the help of system call. And that is exactly what we are going to decode in the next video. So till then, stay safe out there, and remember, we will keep it simple.